Okay, so as I said, my name is Lisa Marshall. I'm the co-director of HeatSmart Tompkins. That's a new role for me. I just started in that job a couple of months ago, and with me also is Jonathan Comstock, who was the program director for several years and is also the founder of HeatSmart Tompkins. We are a community nonprofit. Our mission is to just do education and outreach around energy efficiency for homes and also for commercial properties, about energy efficient home heating solutions such as insulating, air sealing, and installing heat pump systems. We want everybody to know about the cost savings, the comfort and health benefits, and the climate solutions that are available to you for your home. We don't make any money off of anything you may or may not buy as a result of our presentations. So our goal is to be your guide. We are a resource for you. Studies have shown that the reason that more people don't have heat pumps in their home in the US is that they don't know about them. Consumers don't know about them, and also HVAC installers don't really know about them or enough about them and all the benefits of them. So we founded HeatSmart to fill that knowledge gap so that heat pumps will become widespread and fossil fuel heating will join the ash heap of history, we hope soon. So we fulfill that role by making sure that there's accessible information to you about all of the options for your home, and we help you to figure out which options might be best for you. That includes providing transparency around the costs and the quality. Not all heat pumps are the same. And we're a neutral source to answer your questions or troubleshoot as you go through the process. That process could start with just learning about what the options are, to thinking about what choices you want to make in your home, to choosing which proposal from a contractor you might want to go with by helping you understand what has been proposed to you, and helping you through the process if you're getting something installed and you have any questions or problems along the way. That's what Jonathan and I are here for, is to help you. So HeatSmart Tompkins was the first HeatSmart program, and we're really proud of that. We started here as Solar Tompkins with a Solarize campaign, and that was so successful that the founders of Solar Tompkins turned their idea to what other community resource on climate solutions could we provide, and we lit upon HeatSmart. At first, we were funded by community foundations, and but quickly New York State NYSERDA, which is a New York State agency funded by all of us on our utility bills, decided that the HeatSmart program was so important that they were going to fund it, and they were going to start HeatSmart programs around New York State. So this map shows some of the other programs, and some of you might on this webinar might be from some of our neighbor programs, the Southern Tier program, the Otsego program, or the HeatSmart Central New York program. And you are very welcome on this webinar as well. Okay, so HeatSmart in the time of COVID, we've had to change our practices. What we really love to do is go out in the community and meet you face-to-face, introduce you to our installers face-to-face. And we can't do that right now. So thus we are hosting these webinars. We also post the webinars on our website. So if you missed a webinar that you wanted to see, it will now be posted on the website. Or if you are telling your friends about the webinar and saying they should watch it, they can watch it on the website. We also now have some video home tours. We've gotten some happy HeatSmart customers to do video in their home and send it to us that we have posted on social media and on our website. And very importantly, we have protocols in place to keep you safe so that the HeatSmart process can go forward for you. Whether you're comfortable with somebody coming into your home or not, you can get a home assessment for free from any of our installers. If you are comfortable with people coming to your home, our installers are taking precautions, taking their temperature, wearing gloves, hand sanitizing, washing their hands, wearing masks, and all of those good things. But if you're not comfortable, they can also give you a very good assessment remotely over the phone. You can send them pictures, they can ask questions, and they can assess your project that way as well. Okay, so that's me. I'm going to stop sharing my screen and turn it over to Jon Harrod to walk us through the do's and don'ts of cold climate air source heat pumps. Take it away, Jon.
Yeah, thanks so much for everyone who's here today. Thank you also, Lisa and Jonathan. Initially, HeatSmart had asked me to do a case study on one of our projects, and I said, hey, you know, I just had written this article on this subject, and I'd really like to present about this. So they very kindly were flexible in allowing me to present this today. For folks that know me and know Snug Planet, they know that we're passionate about air source heat pumps. We just think, you know, these have so much potential. They're flexible in their application. They're very efficient in both heating and cooling modes. They can be a very cost-effective choice, especially when you're replacing an expensive fuel like oil or propane or electric resistance. And all in all, they really are the most scalable path towards a low carbon housing stock. So we really feel that the work that the HeatSmart programs are doing and the stuff that we're out there doing every day is really on the right track to getting fossil fuels out of people's homes. So that's the good news. The bad news is that these systems can be really unforgiving when it comes to poor design and workmanship. And if you don't get these right, you'll end up with poor temperature control, excessive noise, inefficient operation, a cycle of callbacks where you aren't able to resolve the underlying problem, and ultimately a short lifespan and a low level of customer satisfaction. And, you know, one of the scary things about scaling something up is if you scale up something badly, you're going to end up with a lot of problems. So one of the things I'm really passionate about is getting things right with air source heat pumps, and it's not that hard to do. I've built on my own experiences, my own reading on this subject. I ended up, when I was sitting at home during the first stages of the pause, writing an article on this and submitting it to the Building Performance Journal, which is a trade organization. And for anyone who's interested, there'll be a link at the end where you can email me and I can send you reprints. So the first big important thing starts back at the design stage, and it's really important to size this equipment correctly. If we put in a system that's too small, and here I'm not talking about physical size, I'm talking about heating and cooling capacity. If it's too small, it won't keep up under extreme weather, and you won't be able to maintain comfort on really hot or really cold days. But bigger isn't always better. If it's too big, you're gonna lose efficiency. You're gonna end up with a system that cycles on and off frequently. You may end up with temperatures that wander all over the place. So the question is, how do we find just right? And to do that, we follow a industry standard procedure. The Air Conditioning Contractors of America created a series of manuals, and the one that we use to determine how much heating or cooling a house needs is their Manual J. It's essentially a spreadsheet where you put in all the characteristics of the house, the window areas, the window types, wall insulation levels, and so forth. And it will tell you, okay, this house needs so many BTUs to keep it warm on the coldest day that you're likely to experience. The better the information that you put into this calculation, the better results you'll get out of it. And that's one of the reasons that we like to, instead of just kind of guessing what a house's air leakage is, actually go and measure it and spend the time to accurately put in the window shading, for example, the overhangs and the things like that that will affect how much sunlight comes into a house on a hot day. So if we can do this calculation accurately, we're going to end up with a system that is correctly sized to the house. Now, most of the heat pumps that we're going to be installing are modulating, which means that they can vary their output across a certain range. And so what we want to do is size the system so that on the coldest day we're likely to experience, the system is running pretty much flat out at maximum capacity. But the lower it can modulate down, the more efficient it's going to be on mild weather when you don't need that full capacity. So when we're picking out equipment, we want to first pick the right maximum output, but then within that, look for ones that have a nice wide range of modulation. Another big lesson that we've learned is don't put ductless heads in small rooms if you can avoid it. This picture comes from one of the manufacturer's websites, and you'll see it replicated all across the internet. And here they've got a ductless head in every single room. This is not best practice. Essentially, the smallest these heads are made is about 6,000 BTUs. But oftentimes, a small room like a laundry room or a home office might need a lot less than that. It might only need 2,000 or 3,000 BTUs. So what can happen is that you have to install an outdoor unit that is pretty close to the sum of all the indoor units. If each of your indoor units is twice as big as it really needs to be for that room, you end up with an outdoor unit that's also twice as big and isn't able to modulate down far enough that when only 1 or 2 rooms is calling for heat, it's able to run efficiently. And so this can lead to all kinds of problems. One of the ways that manufacturers get around this is that if, say, this laundry room is only calling for 3,000 BTUs, but the outdoor unit can only modulate down to 8,000, those would be pretty typical numbers. The outdoor unit has to bleed refrigerant through the other heads, and that can create unexpected hissing noises. It can wake people up in the night. It can also mean that you're putting heating or cooling into rooms where you don't want it. So we want to avoid this practice of putting heads in every room. There are some ways that we can get around that. A couple solutions that we frequently use. One that we really like a lot are these compact ducted heads. So instead of a ductless head in each room, we might have a compact ducted system, which is what you see here. It's essentially a little air handler that's hooked up to a very compact duct system and provides heating or cooling to one part of the house. In this case, this was a cute little 3-bedroom ranch, and we put a high wall head, like you saw in the previous picture, in the great room, which served the great room, dining room, kitchen area. And then for the bedroom wing, we put in this compact ducted air handler. It had 3 short duct runs that went to each of the bedrooms. And now, instead of having a 6,000 BTU head in each bedroom, we've got a 9,000 BTU air handler that splits its output between these 3 different rooms. So this is a really great solution. You have to have a place like a basement or a conditioned attic to put it. Another solution that we've used for very small rooms like bathrooms is to just put a small length of electric baseboard or a radiant towel rack or some other low output, low consumption heater in those rooms. They really don't need cooling. They can get that passively from the adjacent rooms. Really important, and everyone who's a HeatSmart installer, I'm sure knows this by now, but it's really important to elevate the outdoor unit above the average snow depth. And the reason that's usually given for this is that you don't want snow drifts to pile up over the unit. These need airflow to function properly. So we need to keep bushes and fencing away from the unit, but we also need to elevate it high enough that it's not going to end up buried in snow. But also really important is that we need to have free drainage under the unit. Because these are extracting heat from the outdoor air, they're cooling the air that flows through them in the wintertime, and so frost forms on the coils. And in cold weather, a couple times an hour, they will have to switch into defrost mode. and that frost that forms on the coils gets melted off and drips away. That's why you need the free drainage under the unit. If that ice starts to build up, it will eventually block airflow through the unit, and in an extreme case could even crush the coils, leading to loss of refrigerant and, you know, kind of catastrophic damage to the system. So having that free drainage under the unit is really important. This is something we did once and we will never do again. You don't want to mount the outdoor unit on a wood frame wall. One of the ways that these systems get their efficiency is that they have variable speed compressors and fans. And so in order to match the heat load of the house as they're modulating, they will ramp up that compressor and that fan over a range of frequencies that might range from, for the compressor, from about 10 cycles per second up to about 120 cycles per second. And somewhere in that range of frequencies is a frequency at which that siding is going to start to vibrate and you're going to get noise complaints. So we really, whenever possible, prefer to mount the unit on the ground like you see here, or if we need to attach it to a wall, we want to attach it to a masonry foundation wall. This is a slide I thought was really interesting. This was done by Stephen Winter Associates that are real building science geeks, and they did this very high-tech test where they taped a piece of cardboard next to a high wall unit and used an infrared scanner to look at the temperatures. And what they found, not too surprisingly, is that the air that's coming into the unit, these units draw the air in at the top, they pass it over the heat exchanger and they blow it out at the bottom. The air that comes in at the top is not representative of the overall temperatures in the room. It's typically a few degrees higher. And this effect is exaggerated when the unit is pressed right up against the ceiling. You don't get good airflow, you don't get good mixing. And so what happens is that you don't get good heat exchange because the air that you're bringing back into the unit is already warm. It doesn't have as much ability to absorb heat as if it were room temperature, you know, 66, 68 degrees. So the solution, if you're going to install a high wall unit, is to install it ideally at least 6 inches down from the ceiling. And that's what we have in this left picture here. Plenty of room for mixing to occur. Because we're primarily a heating climate rather than a cooling climate, in some ways it's actually even more ideal to have our heat emitters low in the room. And these are a solution for that. These what we call floor units. They're actually attached to the wall just a few inches above the floor, but they're pulling in the coolest air close to the floor and heating it, blowing it out. They work fine for cooling in our area. The main reason I think we don't install more of these is that people tend to have more free wall space higher up in the room, and most of the space low in the room is covered with furniture. So this is another really important thing that I think sometimes gets missed, which is properly sealing the places where the refrigerant piping and the control wires go through the house. Heat pumps move heat in and out of the house using refrigerant that travels through copper pipes. And there's also control wires that carry signals back and forth between the indoor and outdoor unit. So there's typically at least one, sometimes more 3-inch holes drilled in the house. And if these aren't properly sealed, first of all, you'll get insects coming in. You'll get air leakage. If you're air conditioning, you can get hot, humid air that comes into the wall cavity. Condensation happens, and then you can get mold problems. And another issue that you run into is that you don't get good temperature control. The hole that allows the piping and the wires to come into the unit is about here. The sensor that senses the room temperature is about here on the unit. So if there's outdoor air leaking in and getting into the unit, it's going to throw the temperature sensing all out of whack. So we really need to do a good job. This isn't the prettiest photo on the left, but it just shows the use of expanding foam used to thoroughly seal that hole where the piping goes in. On the right, we have a device called a wall sleeve, and we strongly recommend that these be installed every time we're running piping through a wood frame wall that's full of something like fiberglass or cellulose, because you can't really get a good seal spraying this spray foam into those soft and fibrous materials. And so we insert this little telescoping sleeve. It forms a nice tight seal and something that holds the spray foam in and gives you a much better seal overall. And they cost about $10 a piece, but they are, you know, a really good thing to add to your work scope. Condensate. As we find that we're getting hotter and more humid summers, we're doing more air conditioning, and managing condensate, which is the moisture that's pulled out of our indoor air in air conditioning, becomes a really important consideration. Backing up to this high wall unit, and I talk a lot about high wall units because they're about 90% of what we install. So the air comes in the top, passes over the heat exchanger, there's a little fan, and it blows out through the louvers. As it passes over the heat exchanger, it's cooled and condensation happens. That condensation runs down to a little drain pan, and then that condensate drains by gravity out of the house and down to the ground. That's a pretty typical installation. It's 100% gravity drained. So in order for that to work properly, we have to pay a lot of attention to the pitch of this condensate pipe, both where it leaves the house and all the way down to the ground. We have to make sure that it's sloping steadily, at least 1/4 inch per foot, all the way down. They do get filled up with algae and spider webs over time, and so we also need them to be accessible so that we can clean them out as part of our annual maintenance. If you have a situation where you can't achieve a good slope with the condensate, you can use a condensate pump. This is a little cutaway diagram showing one type of aftermarket condensate pump. So the condensate in this picture would be coming into this device that attaches onto the bottom of the unit. And in here is a little pump. It's very similar to like a pump that you'd have in a fish tank or something like that. It also has a switch so that if for any reason it fails, it stops the unit from operating and making a big mess all over your interior of your house. This condensate pump can push this condensate up and into the attic and over to some easier to drain location. So this is another great solution. The one I have shown here attaches onto the bottom of the head itself. There are some that are small enough to actually fit within the head itself. So one of the things that, you know, I've been really talking and writing a lot about lately is refrigerant leaks. Refrigerants are what make heat pumps work. They absorb heat and they release it very efficiently depending on the pressures that are creating in the system. So they can move heat into the house in the winter and out of the house in the summertime. The problem is that refrigerants, if they leak out, the system doesn't work. And if they get into the atmosphere, they themselves are very potent greenhouse gases. The ones that we use today have global warming potentials several hundred to 1,000 times the same amount of carbon dioxide. So for a lot of reasons, we want to make sure that these refrigerant lines are 100% tight. And to do that, we really need to focus on flaring technique. A flare is the way that we attach refrigerant lines in heat pump systems for the most part. There's a few other options, but flaring is the dominant technique. So what we have here is a little cone of copper that we forged with a tool. It presses onto a brass cone, and then a flare nut slides over the whole assembly and tightens it down, forming a mechanical seal between the copper and the brass cone. If that nut is not tightened enough, we get a leak. If it's tightened too much, it'll actually crush this flare and we'll get a leak. So we have to get that just right. And the only way to get the torque on these flare nuts just right is to use a torque wrench. There's different torque settings that are needed for different types of tubing. So the smaller tubing that we use, the 1/4 inch tubing, only needs about 13 foot-pounds of torque. But the larger tubing, the 5/8 tubing, needs 50 pounds of torque. So if you can imagine, you know, kind of the different level of force that you'd need to lift a 13-pound dumbbell versus a 55-pound dumbbell, and then try to imagine doing that just based on feel, you'll understand quickly that it's not possible. Instead, we use these torque wrenches, and you set them to the desired torque, and then you tighten the flare nut, and when you reach the desired torque, you hear a click and you stop. And this is the way to know that we're getting the correct tightness on these flare nuts. And then, you know, for all the reasons I mentioned, we want to do everything we can to avoid refrigerant leaks. What we've kind of reached consensus on is that there really needs to be 4 separate steps to your leak testing in order to eliminate the vast majority of these leaks. And one of them is to fill the copper tubing that you've just installed with 500 psi nitrogen and make sure that it holds that pressure. Some manufacturers will recommend a 24-hour test. We've concluded that the test can be much shorter as long as you go through and you apply this bubble solution, which is what I'm doing here, to all the joints in the system. Check to make sure that no bubbles are forming, which would happen if that nitrogen was leaking out through the flares. Then we have to evacuate the system to get the air, the nitrogen, any residual moisture out of the system. And that's an important step in startup. But it gives you one more chance to check the tightness of the system. You evacuate the system down to a really deep vacuum, almost as deep as outer space. And then you make sure that it's able to hold that vacuum for a certain amount of time. And then once we actually put the refrigerant into the system, we go back and we do one more test. There are a few points in the system that you can't test with these other methods, like the actual valves that you connect to the system. And so we'll go through at the end with an electronic leak detector and pass a little wand over these spots and just make sure that there's no leaks at all. Line set insulation. So the copper tubes are called line sets. And we've just expended a bunch of energy to extract heat from the cold outdoor air. We don't want to lose that heat back to the outdoor air by having lousy insulation like you see here on the left. We want to make sure that that insulation is done really thoroughly, all the way from the outdoor unit to the indoor units. In air conditioning, if we have bad line set insulation, we can get other problems. We can get condensation inside walls and other things like that that can cause a lot of headaches. And then the last thing, and I think one of the things that's most often neglected, is to do good customer education. You know, our installers are good installers. They're not necessarily good educators. And they're often finishing up these jobs at the end of a long day and don't necessarily, historically have not always left the homeowner with everything they need to know about how to operate the system efficiently, what maintenance is needed, and so on. So I think a place that many installers, including us, could really raise their game is to increase customer education. I also think HeatSmart plays a real valuable role in this as well. The education starts during the sales and design process, where we, work with the customer to make sure we really understand what their needs are, and also make sure that we have realistic expectations about what installing a heat pump is going to do to their fossil fuel bills, how much it's going to reduce those, how much it's going to increase your electric bills correspondingly, what the noise level is going to be like with these systems. They are very quiet if they're installed properly, but they're not 100% silent. They operate a little bit different than the fossil fuel systems people are used to. We always used to advise people with gas or oil furnaces, if you're going away, you're going to work, turn your furnace down, turn it down 5 or 10 degrees, and set a programmable thermostat so it comes on half an hour before you come home. And with a fossil fuel system, especially an oversized one that could recover very quickly, that was a great way to save energy. Heat pumps operate a lot more efficiently if you leave the temperature alone. We recommend, we say, set it and forget it. That allows them to stay in the middle of their modulation range, kind of just cruising along, kind of like a car at a steady highway speed, rather than trying to really floor it to bring your house back up to temperature after it's been in a deep setback. And then just making sure that people know what maintenance and service is expected. It's not unusual to get a call or go to an energy audit and see someone that had a heat pump installed 5 years ago, and you ask them, oh, has this been serviced? And they're like, oh, do we need to service it? Do we need to clean the filters? Yes, if you want these things to last a long time and operate efficiently. And that's not a homeowner failure, that's a contractor failure. If we're not educating people about the right way to take care of this equipment, we're not going to get good results. One of the things that we've done to help our installers do a better job of education is create a one-page quick guide. It kind of boils down the frequently asked questions and the most important operating modes that you'll be using with your system. It's a lot easier to navigate than the the 15 or 20 page manual that comes from the manufacturer, and also kind of steers homeowners away from functions that don't really make sense in our climate. Just to share here, for anyone who's interested in learning more about these subjects, here are some resources that have been really useful to me. The Northeast Energy Efficiency Partnership, which is the group that certifies cold climate heat pumps, also has some excellent guides on sizing, installing cold climate heat pumps. A lot of the recommendations here are right out of their guidelines. Green Building Advisor is a great discussion group and subscription site for discussions on energy efficient building, and there's a lot of discussions on there on cold climate heat pumps. The Stephen Winters group study that I mentioned, where they were looking at, they looked at a lot of things, including airflow and overall efficiency of cold climate heat pumps. There's a link to that here. I strongly recommend anyone that's installing these go to every manufacturer's training you can. A lot of these are given locally in Syracuse and Rochester and Elmira. Each one is a little bit different, and each time you'll go away from it with some new piece of information that's going to help you do a better job. And then the article itself that I wrote on this is behind a paywall, but I am allowed to mail out reprints to anyone who's interested. So please don't hesitate to email these to me, and I will get a reprint right out to you. That's it. I think we have some time. Yeah, we have some time for questions, and I'll stick around as long as needed.
Thank you so much, John. Can you unshare your screen so we can all look at each other?
Yeah.
That's terrific. Thank you. that I learned a lot, and I can't wait to hear what people's questions are. So the rest of this webinar time is for all of you who've joined us to ask your questions of Jon Harrod, and Jonathan and I and Lindsay are also here to answer questions about the HeatSmart process. So who wants to kick that off?